Have you ever looked at a sapphire and wondered what gives it that deep, incredible blue? Or how about this? How does a single molecule in your blood carry oxygen to every single cell in your body? Well, the answer to both is a fascinating class of molecules called coordination compounds. They are, you could say, the secret architects behind some of nature's most vital processes and most vibrant colors. So in this explainer, we're going to deconstruct how these amazing molecules are built and, why they're just so important.
Okay, so to get what makes these compounds so special, let's start with a really simple comparison. On the left, you've got a double salt. Just think of it like two simple salts kind of mushed together. When you dissolve it in water, boom, it completely breaks apart into all its individual ions. But then on the right, you have a coordination compound. Now, it's also a salt, but when you put it in water, only part of it breaks away. The core structure, that bit inside the square brackets, it stays totally intact. It's stable.
So that's the big question, right? That's the mystery we're going to solve. If they're both basically salts, why do they act in such dramatically different ways? Well, the answer is all in how they're built.
So, here's our roadmap. We're going to start by looking at what really sets these compounds apart from simple salts. Then, we'll meet the key players. After that, we'll get into the rules of how they're put together, explore the theories that explain their awesome shapes and colors, and see how the same parts can build totally different things. And finally, we'll see these compounds in action all around us. So what is the secret to their stability? The reason they don't just fall apart in water? It all comes down to a really special kind of chemical bond that holds that core structure together like superglue. To get that, though, we need to meet the key players. All right, so what are these things actually made of? To understand that special superglue bond, we've got to meet the two main components. The best way to think about it is like a central hub with a bunch of things attached to it. You've got a central atom and then the molecules that bind to it. First up, right at the very heart of it all, we have the central metal atom or ion. This is usually a transition metal, and its whole deal is that it has these empty parking spots, or orbitals, that are just ready and waiting to accept pairs of electrons. It's the absolute core of the whole structure. And what attaches to that central metal? Well, those are the ligands. A ligand can be any molecule or ion that has a spare pair of electrons it's willing to donate. When a ligand donates its electron pair into one of the central metal's empty orbitals, they form this strong directional bond. We call it a coordinate covalent bond. And that, right there, is the superglue that holds the whole complex together. Now, ligands aren't all created equal. We actually classify them by how many points of attachment they have to the metal. The simplest ones are unidentate, which literally means one tooth. They just bite onto the metal at one single point. Then you get bidentate, or two-toothed ligands, and these guys grab on in two places, kind of like a claw. Some are even polydentate with many teeth, and they can wrap around the metal ion completely. And finally, you've got these tricky ones called ambidentate ligands. Think of them like a tool with two different ends. They can attach using one atom or the other, but never both at the same time. Okay, so we've met the key players. Now let's see how they actually get put together. It's not just random. There's a really beautiful logic to it that was first figured out by a chemist named Alfred Werner more than a century ago. Werner's brilliant idea was that metals have two different kinds of bonding capacity. The primary valency, that's what we usually think of as the metal's charge, its oxidation state. But the really important one here is the secondary valency. This is simply the number of ligands that are directly stuck to the metal, and it's this number that dictates the final 3D shape of the entire structure. And just to make sure chemists all over the world can talk to each other about these things without getting confused, there's a systematic set of rules for naming them. You always name the positive part first, then the negative. Inside the complex itself, you list the ligands alphabetically, then the metal, and you finish it off by stating the metal's oxidation number in Roman numerals. It's like a precise language just for describing these intricate structures. All right, now for the really cool part. How do we explain their very specific 3D shapes and their, let's be honest, often stunning colors? For that, we're going to need a couple of really powerful theories. So, our first tool is valence bond theory, or VBT for short. Its big idea is something called hybridization. Imagine the metal has a few different types of those parking spots, or orbitals, for electrons. Well, hybridization is just the process of blending these different spots into a whole new set of identical ones, all perfectly shaped and angled to bond with the ligands. And that is what determines the final geometry of the complex. So let's see VBT in action. Here we've got the electron set up for a nickel ion. Now, when it reacts with a strong ligand like cyanide, that ligand is powerful enough to actually force nickel's electrons to pair up. This frees up an inner orbital for bonding, and the result of mixing that specific set of orbitals is a flat, square-shaped molecule. But watch what happens with a weak ligand like fluoride. It's just not strong enough to rearrange the cobalt's electrons and make them pair up. So, because those inner orbitals are still occupied, the complex has to use a different set of orbitals from further out. And this different mix results in a totally different 3D structure, in this case, an octahedron.
So, here's the crucial point. Valence bond theory is fantastic for predicting geometry and some basic magnetic properties, but it has some major limitations. And the biggest one, it says absolutely nothing about why so many of these compounds are so intensely colored. It just can't explain it.
So, to solve the puzzle of color, we need to upgrade our thinking. We turn to crystal field theory, or CFT. This theory kind of ignores the whole sharing of electrons thing and instead just focuses on the straightforward electrostatic interactions between the positively charged metal ion and the negative charges of the ligands. And right here, this is the magic of crystal field theory. It predicts that as the ligands get closer to the metal, their negative fields start to repel the electrons in the metal's d orbitals. But here's the thing. Not all the d orbitals are affected equally. Some get pushed up to a higher energy level, and others get pushed down to a lower one. This creates an energy gap. Now, when light hits the complex, an electron can absorb a specific color of light to get the energy to jump that gap. And the color we see? It's the complementary color that wasn't absorbed. That's it. That's the origin of color. Okay, so we've seen how the rules of assembly create these specific shapes. But believe it or not, the complexity doesn't stop there. What happens when you can build more than one unique structure using the exact same set of chemical parts? Well, this whole phenomenon is called isomerism. Isomers are compounds that have the exact same chemical formula, but a different arrangement of their atoms in space. It's like having the same box of Legos, but building two completely different models. And each model has its own unique properties. And this slide right here shows brilliantly why this matters so much. On the left, in what we call the cis arrangement, you can see the two green chloride atoms are on the same side of the central platinum atom. This molecule is cisplatin, and it's a powerful anti-cancer drug. Now look to the right. In the trans version, those same two green chloride atoms are on opposite sides. This tiny change makes the molecule completely biologically inactive. Same parts, different arrangement, a literal life and death difference. So, after all this theory, why does it all matter? It matters because these compounds aren't just curiosities in a textbook. They are, quite literally, everywhere. They're running the world around us and inside of us. Let's just do a quick run-through. The red in your blood, that's hemoglobin, an iron coordination complex. The green in every single plant leaf, that's chlorophyll, a magnesium complex, turning sunlight into energy for all of us. Vitamin B12 is an incredibly intricate cobalt complex. They're used in old-school photography, in industrial catalysts that make modern life possible, and they're even the reason your water is hard or soft. So, from the most fundamental processes of life to the technologies that shape our entire world, coordination compounds are the silent, elegant architects. Understanding how they're built is the key to understanding our world. And that leaves us with one last, really exciting question. Now that we know how they work, what new materials, what new medicines, and what new technologies will we build with them next?